Hello, I am Dr. Imran Khan. Today we are going to discuss fabrication of integrated circuits. With rapid miniaturization and efficient high volume processing, over billion transistors are produced for every person in the world each year. Massive integration of transistors has made complex circuits in the form of integrated circuits inexpensive and a wide range of electronic application practical and affordable. The complexity or density of integrated circuits is sometimes decided by the names LSI, VLSI, ULSI, GSI. LSI is large scale integration and we have around 10,000 transistors. VLSI stands for very large scale integration, around 1 million transistors. ULSI stands for ultra large scale integration. GSI stands for gigascale integration. In actuality, all these terms are used to describe circuits and technologies of wide range of size and complexity and simply means large integrated circuits. Introduction to device fabrication. Semiconductor companies produce most of the silicon wafers used in the world. Hundreds of silicon device fabrication lines purchase these wafers as their starting material. A large wafer fab can produce around 40,000 silicon wafers into circuits each month. So in this slide, we will show you a simple example of device fabrication process. So it includes formation of SiO2 layer. Here we call it oxidation. Its selective removal or lithography and etching. Introduction of dopant atoms into the wafer surface or ion implantation. So here you can see dopant atoms are introduced into exposed silicon. So this is called ion implantation. And the fourth one, dopant diffusion into silicon. So we also call it annealing and diffusion. So here, combination of all these and other fabrication steps can produce complex devices and circuits. This step-by-step and layer-by-layer method of making circuits on wafer substrate is called planar technology. Oxidation of silicon. In integrated circuits, silicon oxide is used for several purposes, ranging from serving as a mask against dopant introduction into silicon to serving as the most critical component in the metal oxide semiconductor field effect transistor. SiO2 layer of precisely controlled thickness are produced during IC fabrication by reacting Si with oxygen gas or water vapors at elevated temperature. So the overall reaction, so here you can see this dry oxidation and the wet oxidation. Growth of SiO2 using oxygen and water vapor is referred to as dry and wet oxidations respectively. Dry oxidation is used to form thin oxide films. Wet oxidation, on the other hand, proceeds at faster rate and is therefore preferred in forming the thicker oxides. Water vapor Water vapors diffuses through SiO2 faster than oxygen. So here you can see this figure 1 and 2. So these show horizontal furnace basically for this oxidation of silicon. So lithography, we can selectively remove oxide from those areas in which dopant atoms are to be introduced. Spatial selection is accomplished using a process called photolithography or optical lithography. So here in the figure you can see this process. Lithography is difficult and expensive. There are around 40 lithography steps in IC process. So here you can see this process. So lithography. So basically in this slide we will discuss major steps in the lithography process. So first, application of resist coating. B, resist exposure through mask and an optical reduction system. So here you can see this whole process. And this C, after development of exposed photoresist. So we have this positive resist and negative resist. And in the end, D, after oxide etching and resist removal. So here we have this whole thing. So you can see in the figure here, etching and resist strip. Doping. The density profile of dopant atom in the silicon is generally determined in two steps. First, the dopant atoms are placed on or near the surface of wafer by ion implantation, gas source doping, or solid source diffusion. Ion implantation is the most important doping method because of precise control it provides. In ion implantation, an impurity is introduced into the semiconductor by creating ions of impurity. Here you can see this whole process. So this ion implantation is basically the dominant doping method. Excellent control of dose, good control of implant depth with energy. So repairing crystal damage and the dopant activation requires annealing, which can cause dopant diffusion and loss of depth control. So here we discuss this doping. Thin film deposition. Silicon nitride, silicon dioxide, silicon and many other type of metal thin films are deposited during IC fabrication. Deposited films are usually not single crystalline. So here we have this examples of thin films in integrated circuits. So some of examples are advanced MOSFET gate dielectric, polysilicon film for transistor gate, metal layer for interconnects, dielectric between metal layers, encapsulation of integrated circuits. Sputtering. Sputtering is performed in vacuum chamber. So here you can see this sputtering process. The source material called sputtering target and substrate holding the Si wafer from opposing parallel plate connected to a high voltage power supply. During deposition, the chamber is first evacuated of air and then low pressure amount of sputtering gas, typically argon, is admitted into the chamber. Applying an inter-electrode voltage ionize the argon gas and creates a plasma between the plates. The target is maintained at negative potential relative to the substrate and argon ions are accelerated towards sputtering targets. So here you can see this all process. So here we have this sputtering target and this silicon wafer. So here you can see chemical vapor deposition. Sputtering is the chief method of depositing aluminium and other metals. Sputtering is sometimes called the method of physical vapor deposition (PVD). While sputtering is relatively simple and satisfactory way of depositing thin films over flat surfaces, it is directional and cannot deposit uniform films of vertical walls of holes or steps in surface topography. This is called step coverage problem. CVD, chemical vapor deposition. CVD on the other hand deposits much more conformal film, which covers the vertical and horizontal surfaces with basically no difference in the film thickness. In CVD, the thin film is formed from gas phase components. Either a component decomposes to form a thin film or reaction between gas components take place to form it. So here in the figure we have a schematic of CVD process. So here we will discuss epitaxy, deposition of single crystalline film. Epitaxy is very special type of thin film deposition technology. Epitaxy produces a crystalline layer over a crystalline substrate. So these figures, this is figure A for epitaxy and this figure B for selective epitaxy. Epitaxy produces crystalline layer over a single crystalline substrate. Figure illustrates the epitaxy process. Selective epitaxy is variation of basic epitaxy technology and it has interesting device applications. In selective epitaxy, deposition and etching gas is introduced to simultaneous etch away the material. The net deposition rate is positive. Atoms are deposited only over the single crystalline substrate. There is no net deposition over the oxide mask because the deposition rate over the oxide is lower than the etching rate. So here we have this epitaxy and selective epitaxy. Interconnects. To build an integrated circuit, the individual devices must be interconnected by metal lines. This procedure is sometimes called metallization. A simple interconnect is illustrated in figure A. First SiO2 is removed. So here you can see. So first SiO2 is removed from areas where contact is to be made with silicon. Then a layer of metal is deposited over surface typically by sputtering. The metal, perhaps aluminum, is then removed from areas where it is not desired by lithography or dry etching. So here you can see this whole process. The metal interconnect in Fig perform the function of interconnecting the two diffusion regions. So here you can see. So in this figure 1 and 2, so here these are basically schematic drawings of device interconnects. So here in the figure A we have basic metallization example, and in the figure B we have this multi-level metallization structure. So let's go to next slide. So in the next slide we have this basically scanning electron microscope image for our multi-level interconnects. Okay, so after removing the dielectrics, so here you can see this whole process. So this is basically multi-level interconnects. So here you can see. Uh, so basic steps of forming a copper interconnect lines using Damascene process. So we are going to explain this copper Damascene process here. So the basic steps include: cover the wafer with dielectric such as SiO2. So here we have this, and B, etch a trench in the dielectric. So here we have this dielectric etching, and in the C, deposit a linear film and then deposit Cu. So here we have this, and in the D, polish away excess metal by CMP. So this CMP is chemical mechanical polishing. It removes unwanted materials. Okay, since a large number of metal layers and process steps are involved, making the interconnects consumes a large part of IC fabrication budget. This part of the fabrication is also called back-end process. In contrast, the steps used to produce transistor are called front-end processes. So here we have this planarization. A flat surface is highly desirable for subsequent lithography and etching. So chemical mechanical polishing is used to planarize each layer of dielectric in the interconnect system, also used in front end process. So in the end, we have this testing, assembly, and qualification. So these are basically the final images of the chip. So so we have wafer acceptance test, dice sorting, wafer sewing, and laser cutting, packaging, flip chip solder bump technology, multi-chip modules, burn in, final test, qualification, and these all things are included in the testing, assembly, and qualification. So in the end we have this lecture summary. For a device fabrication examples from step 0 to step 13. So I'm going to explain it. So first of all, you should have this silicon wafer, and the first step is the oxidation and then lithography. So here you can see etching. So here this image is showing the etching process, and then the fourth one is ion implantation. So here you can see the fifth one is annealing and diffusion. The sixth one is sputtering, and the seventh one is lithography. So here you can see the eighth one is metal etching. Ninth is CVD, nitride deposition. 10th is lithography and etching, and the 11th is backside milling. So here you can see The 12th is backside metallization. So here you can see this backside metallization, and the final one is dicing, wire bonding, and packaging. So these all steps are included in the fabrication of integrated circuits. So this was all for today. So if you have any question, please feel free to contact me. And uh, thank you very much for today. See you next time.